Hello, my name is Tal Ridnik, I'm from Alibaba, Israel, and today we're going to talk about TResNet high-performance GPU dedicated architecture. We start by asking, what do we really want the backbone to be? Most academic articles will focus on the accuracy and maybe on the inference throughput. However, deep learning practitioners have other needs. They want the backbone to have high training throughput, they want it to support large batch size, they want it to be easy to train, and they want the backbone to have fast and consistent convergence along with other miscellaneous. In the table above, we compare architecture with similar accuracy in ImageNet, and we see that ResNet 50 provides double the training speed compared to more modern architectures like EfficientNet and MixNet. The reason for this? Flops optimizations. Modern models try to optimize the model flop versus accuracy. Flops are a bad proxy for GPU throughput, because GPUs are usually limited by memory access cost, and not by the number of computations, which is what flops measures. So this was our motivation to develop TResNet, a family of GPU-dedicated backbones. Since we saw that ResNet 50 works well, we start from its basic design, and on top of it add modern refinements and novelties that actually improve the speed-accuracy trade-off. So let's talk a bit about TResNet refinements. The first refinement is the stem unit. We replaced the traditional ResNet 50 stem with a novel space-to-depth based stem. This new stem design is faster, but surprisingly it also improves results, mainly because it can minimize the information loss during the initial downscaling. The second refinement is a block type selection. ResNet 50 uses solely bottleneck modules, while ResNet 34 uses basic block modules. In TResNet, we found that a better speed accuracy trade-off is gained by mixing the different blocks along the network. We also replaced the simple strided convolution with anti-aliasing downsampling scheme to further minimize the information loss during downscaling and to improve results. Another change in TResNet is replacing all batch noise in the network by in-place activated batch nom. This enables us to practically double the maximal batch size to 512 with negligible GPU overhead. We also placed highly effective Sweden excitation layers along the network with some optimizations. We try to choose the best locations of the layers for each block, and also to use the optimal reduction factor for each excitation layer. And finally, we identified that a high-performance network needs a high-quality code. So we used many code optimization, JIT acceleration of different models, dedicated design of global average pooling layers, and wide usage of in-place operations, and more. Now let's talk a bit about the article results. In this table, we compare one variant of TResNet, TResNet M, to ResNet 50. We can see that both architectures have similar GPU throughput, but TResNet M has significantly higher top 1 accuracy. Finally, we have a backbone which achieves a better speed accuracy trade-off compared to good old ResNet 50. In this graph, we see that all along the top 1 curve, TResNet variants achieve better scores than EfficientNet variants. We also tested TResNet on transfer learning tasks. TResNet is a backbone and a simple, effective training scheme. We were able to reach state-of-the-art results on highly competitive single-label datasets like C410, C4100, and Stanford cars. Finally, I want to share some real-world results. Here are results from SodaBench, where repositories around the world benchmark their models. We can see that TResNet models give by far the best speed accuracy trade-off. Another type of real-world result is Kaggle Competitions. Last year we participated in 3 major Kaggle competitions against hundreds or thousands of competitors. With TResNet as our backbone, we were able to reach top places in all of these competitions, demonstrating the backbone effectiveness in highly competitive environments. Thank you.